Okay, so, like I promised, we're getting into the fast-growing hierarchy now. So fast-growing spell hierarchy. All right, fast-growing hierarchy. So we're going to start at the very beginning. Good place to start with f naught of a. So f naught. In case you're not familiar, in mathematics, when you put a 0, you often call that naught. So f naught a is the same as saying f with a little 0 in the subscript here of a. So this is a really, really simple function. Basically, like I said before, the function even more primitive than addition is successorship. So when you have this function here, all this is you take a plus 1. That's what this does. So anything you plug into here, the f0th function just takes this number and adds 1 to it. So if I were to have like f naught of 3, it's going to be 3 plus 1 equals 4. So simple, simple, simple. Now the power of this function comes with recursion, and we get an idea of this when we go to the next number of the function. So f sub 1 of a is going to equal a copies of f0. So we take this number minus 1, so f0 of f0 of f0, blah, 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 a times of f0 of a. So that's what that is. Another way to note this too is you can put a little a up here. So this means a copies of the previous f function, which in this case is 0 because 1 minus 1 is 0, of a. That's another way of writing it. So we'll do an example with this one. So if we have f1 of 3, what that's going to be is it's going to be 3 copies of the previous f function, which is f sub 0. So we're going to have f0 of f0 of f0 of 3. All right. So f0 of 3, we know what that is. This is the successor function. So we're going to get 3 plus 1, same function as this, is equal to 4. So let's just write a little 4 above this, whatever. So 4 is going to be in this bracket here. Now we're taking f0 of that whole thing. So f0 of 4, well, that's just the successor of 4, which is 5. So we'll put a little 5 above here. f0 of 5 is going to equal 6. All right, so what's happening here? In the f1 function, we started with 3, and we got an output of 6. Essentially, this is a doubling function. So let's say we have f1 of n. Another way of writing this would be that this is simply 2n. Whatever number we plug into here, we're going to get 2n. So imagine if we put a 6 in here. Same thing would happen, except this time you'd get 6 copies of the f0 function in the little 6 here. So you go 6 and you go 7, 8, 9, 10, 11, 12, whatever, because you'd have 6 of them adding up instead of 3. You get 12. So the same thing. This is a general thing that works. This is exactly what this function equals. Like eventually, when this gets a little bit higher, we're going to have to use approximations because the numbers are going to be too big to calculate. But for now, this is an exact equivalence. So f1 of n is equal to 2n. So let's move on to f2 function. So f2 function of a is going to be the same thing as before. We're going to take that many copies of the function into the previous function. So we'll do an actual example. So f2 of 3, we're going to take 3 copies of the previous f function. So f1 of f1 of f1 of 3. Well, we know this is a doubling function. So f1 of 3 is going to equal 6. f1 of 6 is going to equal 12. And f1 of 12 is going to equal 24. And what's happening here, another way to write this is we can go 2 to the power of n times n. So I'll just explain that a little bit. Basically, we're doubling each time. And another way of saying doubling is 2 to the power of how many times you're doubling. Then we have to multiply by n because this is the original number that we're starting with, whatever. So let's try that out. Let's see if it works. So 2 to the power of n times n. In this case, it's 3. 2 to the power of 3 times 3. 8 times 3 is equal to 24. Check. All right, that works. Now, as we go further up, like to the 3 of n is something like this, with a tower of n 2's. Power of n here, and then it what's it called? It has a bunch of other stuff here. Like it has a bunch of other functions that continue on, because like this little remainder here or whatever, the same thing happens. So you get kind of a general function. This is where the power of the function comes from. Like the majority of the value of the function is going to come from here, and you tack on a bit extra here. It's going to be the same thing. Like this is a big tower of 2's, and you're going to have some other stuff here. But instead of calculating all this out, we want kind of just an approximation. It's going to be good enough. And that approximation is going to be our arrow notation. That's stuff that we learned from before. So in general, let's say we have Fm of n. That is approximately 2 with m up arrows of n. Now, this isn't going to be a very good approximation in the lower numbers, but as you get higher up, the differences don't make much, it doesn't make much difference, and this becomes a fairly good approximation. So we'll be able to use this whatever as an approximation for fast-growing hierarchy. So you can kind of see what my motivation for introducing new up arrow notation. If we were to just use our high school knowledge of big numbers, we would run out of steam right about here. Like this is where exponentials even don't account for the power of this function. We don't really want to run out of steam at an easy little f3. So at least now we can figure out vaguely what numbers, like let's say we have an f100 of whatever, 3 I guess. We know that that'd be roughly 2 with 100 up arrows, 3, which is a pretty big number. Considering like 3 quadruple up arrow 3 was that giant huge number that we had to express with a tower of 7.6 trillion 3's, that many iterations of double up arrow operation. And now imagine having like 100 up arrows. It could be insane. It's nuts. So this already is a huge number. And it seems like it kind of gets arbitrary at this point, because we can keep on just upping this number here and putting bigger numbers into the fast-growing hierarchy. So what we're going to do is we're going to introduce another concept which is going to make this even more powerful. And this is the idea of infinite ordinals. Okay. So infinite ordinals. So our first infinite ordinal that we're going to use is small omega, not to be confused with W. And basically this is an infinite number, but it's a very special infinite number. It's an infinite number where the order of it matters. So that's a little confusing, but if you were to think of just regular infinity that you're used to, that's what's called cardinal infinity. And you can kind of think of it as just like a bag of things. Like you have this thing and there's just a whole bunch of stuff in it. Doesn't matter what's where, it's just an infinite bag of things. You can throw things into the bag and it's still going to be infinity. So if you have like infinity and you put one more thing in the bag, it's still going to be infinity. This is a special kind of infinity because it has strange properties. Omega plus 1 does not equal 1 plus omega. In this case, this is infinity plus 1, but it's bigger than this, which is just going to equal infinity. Now that seems very strange, but so let me write it down in some way that might be a little bit more easy to understand. If you think of this in terms of a set, if I write down 1 plus infinity, let's take infinity. Let's just have a bunch of numbers here. So 0, 1, 2, 3, 4. We imagine it's going off into infinity. Let's add one more number in the beginning. It doesn't matter what it is. It could be anything, but let's just say it's 0. Like what really matters is that I'm putting an object into the set. It doesn't matter what the number is. So I put an extra object into the beginning of the set. Well, this is still just an infinite set. Nothing has changed. So this is still omega. But what if I do omega plus 1? Okay, well I have my set. 0, 1, 2, 3, 4, blah, 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 blah. Okay, well the order matters this time in ordinals. So I have to put this 1 at the end. It can't just go anywhere in there. So how do I do that? How do I put something at the end of an infinite sequence? Well, it has to be its own thing. It has to be its own set. So we end up with two sets instead of one, and this is different. So this ends up being bigger than this one. The same thing goes with if I want to take omega times 2, I have to do it this way, because this does not equal 2 times omega. And the reason for this is if we were to figure out 2 times omega, let's say we have a set of 2, like 0 and 1. That's our set of 2. If we times that by infinity, we basically get 0, 1, 0, 1, 0, 1, 0, 1, infinite number of times, which is just an infinite set. Nothing has changed. It just equals omega. But omega times 2, what we have there is 2 separate infinite sets. And that's different. That is bigger. So making the order matter, you can get all kinds of crazy things where infinity plus 1 is bigger and this is different than that. All kinds of crazy stuff. Now this still might be a little bit confusing, but you'll see how this is useful when put into the context of the fast-growing hierarchy. Okay. So we're going to stick this in now. And it's as simple as this. Just like we put a number in the subscript of the fast-growing hierarchy, we can go f sub omega of a number. And I like using 3. So one property of infinite ordinals is that we can do something called diagonalization. Now, without getting into too much math about diagonalization, basically it's as simple as taking this number and replacing it in here. So this would be simply f3 of 3. And if it helps, you can kind of think of this infinite number as a container for a number. And in order for that container to be big enough to hold all these huge numbers we're going to have, it's necessary for it to be infinite. So if that kind of helps you, then you could think of it that way. But basically you just stick this number in here, nice and easy. But that seems a little strange because what have we really gotten? I mean, last example I used, where I had like f100 of 3 or something like that. Well, we're still just getting little numbers. I mean, I can plug 100 in here, and I can do f100 of 100. And that's a pretty big number, but it still hasn't really gotten us any further. I could have just stuck the 100 in here. Where the power comes from is using things like that omega plus 1. Because let's give it a try. Let's what happens when we do f omega plus 1